So we've got the observer standing in the air above the water, and then in the water, we've got this fish. And if the observer is looking at the fish, we can treat the fish as the source of rays of light. And in order to see a ray of light, where does the ray of light have to get to?
Your eyes?
Yeah, got to get to the observer's eyes or your eyes. So let's say we've got rays of light coming from the fish. We're treating the fish basically as a single point here. So we've got rays of light coming from the fish, but they're not just going to go straight to your eyes, because as soon as the ray of light hits the surface, what's going to happen?
It bends.
Right. So let's say we've got a ray of light going kind of towards your eye, but as soon as it hits the surface, that's going to bend because of refraction. So if we put in a normal line here, there's a line perpendicular to the surface. There's our normal line. We currently have an angle that this ray of light makes with the normal line. So this would be θ1. If we're going from water to air, what would you expect to happen to that angle?
It's going to move away from the normal.
Yeah, the ray of light bends away from the normal, making the angle bigger. Exactly, the angle is going to get bigger. And if you have trouble remembering that, I usually look at it in terms of speed. As light goes from water to air, the speed is increasing, so we should expect the angle to increase also. Instead of continuing in a straight line, it's going to bend to make the angle bigger. We're going to end up with a larger angle. So this angle is going to be larger than the angle it came in at. And you can get that exact value by Snell's law, or you can just conceptually look at it as the speed increases, the angle also increases. So this ray of light isn't actually going to get to the person's eyes at all. Instead, we're going to need to look at a different ray of light. Let's say we look at presumably a ray of light that's kind of higher up. Maybe this ray of light. If we put in a normal line at that location, and we can choose any direction we want because we are assuming the object is emitting rays of light in all directions. So this angle, we still expect the refracted ray to be at a larger angle. It's still going to bend away from the normal. But if we set this up right, we can have if we have exactly the right angle of incoming ray of light, then the light is going to bend so that the refracted ray hits the person's eyes. That means the person actually sees it. But the person doesn't think of the fish as being at this location. Because if you ignore what's going on under the water, just ignoring what's underwater for the moment, your brain intuitively assumes that light always travels in straight lines. So if you backtrace this, your brain assumes that the light must have come from back here. Your brain thinks, oh, I'm getting a ray of light from a report from the eyes of a ray of light coming in this direction. That ray of light must have come from way back here. But if we take a look at what's going on, that's not where the light actually comes from. But since that's where the light seems to have come from, what do we call a point that the light seems to have come from? In the language of optics, what do we call the point that the final rays of light seem to have come from?
The image?
Yeah, that is exactly the image. So your brain thinks it sees a fish over here. There's no actual fish there. That is just the image of the fish. So when you look into the water, you think you see a fish way over here at the location of the image, even though there isn't actually a fish there. The fish is actually here, but the way it's emitting light and the way that the light bends make you think the fish is over here instead. So if you're trying to stab this fish with a spear or something, and you throw your spear at the location you think you see the fish, are you going to hit it?
No.
No, because that's not where the fish actually is. If you take your spear and you throw it along this line, you miss. You don't hit the actual fish at all. What this is going to look like from your perspective, if the spear is traveling in a straight line, it's going to look to you like the spear hits the water and bends away from the fish. Of course, the spear isn't actually bending. The spear is going in a straight line, but your perception of the spear is inaccurate because you're looking at bent light. So instead, if you want to actually hit the fish, where should you aim?
More downward.
Yeah, you want to aim downwards from what you actually see. And keep in mind, you can't actually see the actual fish. You're not seeing the actual fish. You're just seeing the image. So what you want to do is, instead of aiming at the image you see, you want to aim a little bit below that, a little bit closer to yourself than the image. And exactly how much closer is really a matter of developing an intuition from years of fishing, I guess. But as long as you're aiming the right amount beneath the image, then when you throw the spear, you're going to hit the actual fish, or at least have a much better chance of it.
Can I ask a follow-up question about this?
Yeah, go ahead.
Okay, so there was one question in lecture where you were looking directly down into the water, right? And then the fish apparently appeared closer up than it actually was, like closer to the surface. And then in this example, we're only looking at distance, but we're not considering depth. And I think I was looking at something online that said that the eye corrects for depth. That's kind of like, I don't know, something I wanted to just ask about.
Yeah, the apparent depth is also going to be different. Here, we're not really looking at distances so much as just where the pink line is the surface normal, just a line at a right angle to the surface for measuring angles from. But yeah, the idea of depth here, the apparent depth versus the actual depth are not going to be the same depth. That if the fish is a certain distance underwater, when you look at it, even if you're just looking at it straight down, so there's no weird displacement of angles thing going on, even if you're just looking straight in, the fish is going to appear to be a different depth than it really is. And it turns out that the ratio of actual depth versus apparent depth turns out to be the same as the ratio of the index of refraction. So if you take the ratio of index of refraction of water versus index of refraction of air, that ends up being the same ratio as the apparent depth versus the actual depth.
So the image of the fish would be higher in this example?
I don't know. I can never remember whether it's deeper or less deep. We can actually figure that out using ray tracing, though. If we take a look at not only, like here we're looking at sort of a ray of light from the front of the fish. But if we also take a look at a ray of light from the back of the fish, let's see if that would work. Or alternatively, I guess we could just draw out another ray of light from the same point. If we draw another ray of light from the same point, like let's say this ray of light, which is not going to hit your eyes. But let's say we draw in another normal line at this new location. And we draw in, again, the angle is going to get bigger. So let's say we draw in another ray. Let's say something like that. So we're saying this angle is going to get even bigger. So what we have here is we've got two rays from the original object that both bend in different ways. If we backtrace both of them, backtrace this one and backtrace this one, then this should tell us the location where where the image of the fish seems to be. So it looks like if we go with ray tracing, I think the image of the fish is going to be less deep than the actual fish, which suggests if you aim at the image, you're going to miss by hitting too high. And also, I guess you could say too far back. So you've got to aim below that. So yeah, it looks like if you've got this fish underwater, the image of the fish is going to be higher up than the actual fish, less deep. And the ratio of image depth versus actual depth should match the ratio of air index of refraction divided by water index of refraction. So I think we can say that image depth over object actual depth, that's going to be the same as the ratio of the index of refraction for air divided by the index of refraction for water, or whatever the materials happen to be. Any questions on that one?
So how do you know it's a virtual image? Is it because you have to backtrace the refracted rays?
Yes, this is a virtual image because the rays have to be backtraced. A real image would be if the rays actually intersect on that other side. So this is going to be a right side up virtual image. And a real image is where the rays of light actually intersect. In this case, the rays of light don't actually intersect, but if we backtrace, they seem to be coming from this point. So we could say that is a virtual image of the fish. Because the rays of light seem to come from there, so it is an image, but they never actually pass through that point, which is why it's virtual. Any other questions on that? All right, then let's try out these problems from the practice file. Pull these up in the chat. Artie, which one from that winter 2019 practice file did you want to try out?
I think for the winter 2019, I think it was like the last problem, or if you have like a better problem for induction, that would also be fine too.
I think this one will actually work pretty well in terms of figuring out how the induced voltage is related to the magnetic field. So let's take a look at that one. Here it looks like we have a train with a magnetic field under these train tracks. So we're looking at sort of a top-down view here. We've got these train tracks, and they're connected by a fixed wire on one side. And then the axle of the train itself is acting as another bar completing the circuit. So we have these rails can be treated as basically wires. We've got this long wire, this long wire, this long wire, and we've got another wire connecting them. And then we've also got this bar that's able to move. So this is basically just a large metal bar that's able to move along the tracks. So those are all wires that can conduct electricity. They form a loop. And the fact that there's magnetic field passing through the interior of the loop means that there exists magnetic flux. And as that bar moves along the track, is flux changing?
Yes, because area is changing.
Right. As the bar moves, we're enclosing more and more area. So that should increase the flux. You could also think of it in terms of as you move this further down the line, there's more and more field lines passing through the interior of the loop. Like if this is very small, only a few field lines. Larger, you get more and more field lines.
So the flux is increasing here?
Yeah, I would say flux is definitely increasing because we're getting more and more field lines passing through the interior of the loop as we make the loop larger. We could also look at this in terms of the flux equals area times magnetic field times cosine of the angle between them. And the angle is just this consistent 0 degrees, because if we draw out a normal vector, what are our options for a direction of a normal vector here?
Also, how would you know where to draw the normal vector?
Normal vector doesn't really have a location. It's just, I usually think of it as being in the center of the area, the center of the surface. But location doesn't really matter here. Direction is what's important. But if we did draw in a normal vector, what are our options for direction?
Would you have to use the right-hand rule?
Not for the normal vector. Normal just means perpendicular to a surface. And the surface we're talking about is the surface enclosed inside this region. Yeah, outwards or inwards would work here, because the surface is within the plane of the screen or the page, whatever you want to call it. And so the only options perpendicular to that rectangle, that region, are straight out or straight in. So that means our options for the normal line, the normal vector, are going to be either straight outwards or straight inwards.
Wait, how do you know the direction could be in the y direction?
What do you mean the y direction?
Like y could be up or down.
Because if it was upwards, like if we have an upwards vector, an upwards vector would not be perpendicular to the surface. The surface we're talking about is the surface enclosed inside the loop. So that surface, if we draw in an upwards vector, that's not a normal vector. It's not perpendicular to the surface. The only way we could have a vector perpendicular to this rectangular surface is if the vector is straight outwards or straight inwards. So you have the option of an outwards normal vector or an inwards normal vector. Either one will work mathematically, but it's easiest to understand what's going on if you choose one that most closely agrees with the existing magnetic field. So I would choose an outwards normal vector here. So that would be our n, our normal vector. And what's the angle between that normal vector and the magnetic field? Yeah, the angle is 0 because the normal vector is in exactly the same direction as the magnetic field. They're parallel, so you have a 0 angle. And cosine of 0 is 1. So if we fill in 0 degrees here, we just get area times magnetic field. So the flux through this loop is area times magnetic field. And based on the dimensions shown, how would we write out the area? Make the normal vector match the you want the normal vector to match the magnetic field as closely as possible. It's not always going to be exactly the same direction. But you're always going to have two options for the normal vector. Whatever surface, whatever orientation the surface is in, you've got two options that are going to be perpendicular to the surface. Like for instance, this surface, you have this direction or this direction as the normal vector, perpendicular to the surface. So normal vector, there's always two options, and it's a good idea to choose the option that most closely aligns with the existing magnetic field. So in this case, we're gonna choose an outwards normal vector. Ideally, you want the angle to be acute, less than 90 degrees. If you choose the opposite direction, you're going to get an angle that's more than 90 degrees. And again, mathematically that works, but you end up with cosine of an angle larger than 90 degrees, which gives you a negative number. And a negative value for flux makes it really difficult to intuitively understand, is this increasing or decreasing? So I find it useful to choose the normal vector that most closely aligns with the existing magnetic field, to guarantee that the angle is less than 90 degrees, which guarantees that flux will be a positive value, just to make it easier to understand what's going on. Any other questions on that so far?
So wait, you said make the normal vector as close as possible to the direction of the magnetic field?
Yeah. Like in this case, the magnetic field is, our options for normal vector are outwards or inwards for this particular loop of wire. The magnetic field is already pointing outwards, so I would choose the outwards normal vector. So
Okay,
this
I
is
know
the-
I asked this already, but how do you know that the direction is going outwards or inwards? For some reason, I'm like fixated on that and I can't really move on with
the normal
the,
vector has to be perpendicular, by definition, it has to be perpendicular to the surface. So if you've got some loop of wire, if you imagine a surface within that loop of wire, like just dip this in bubble soap and it's got a surface enclosed inside, then the normal vector has to be perpendicular to that surface. So for instance, if I had a loop of wire held like this, the surface would be horizontal, so the normal vector would have to be either straight up or straight down. If I hold the loop of wire like this, then the surface would be like this way, basically I guess you could say the YZ plane. So the normal vector would have to be like this, perpendicular to the surface, so left or right. In this case, though, the loop of wire is oriented like this. We've got this surface. The only options perpendicular to this surface are straight in or straight out. So that has to be, those are the only options for the normal vector here.
okay, that makes sense. I wasn't imagining that this was a 3D. Why? Okay,
Yeah.
this makes sense.
And magnetic fields are kind of awkward there because we've been working almost exclusively in 2 dimensions previously, but magnetic fields require a third dimension. In a 2-dimensional universe, magnetic fields wouldn't really work. You got to have a third dimension for magnetic fields to make sense. In this case, though, we've got cosine of 0 because we're choosing a normal vector that happens to be exactly in the same direction as the magnetic field. And how would you write the area enclosed in this rectangle? Based on the dimensions shown here. Yeah, length times width. And so we've got L sub 0, which is the, actually, I guess we should probably treat L as a variable. L sub 0 is the initial length, but L is changing as the bar moves. So L times W. So that means the flux is going to be L times W times magnetic field. And let me go grab a capital phi to use here. Okay, so flux equals length right now, which is changing, times width, which is constant. That's just the distance between the rails, times the magnetic field. So that would be the flux right now. But according to Faraday's law, the induced voltage is not so much about how much flux there is. Induced voltage is about how fast the flux is changing. So Faraday's law is that the induced voltage equals negative change in flux over change in time, or specifically the derivative of flux with respect to time. So to figure out how much voltage we get in this loop as a result of the induced effect, we need to take the derivative of flux. So derivative of flux with respect to time. Of those 3 quantities we're multiplying, though, what's the only one that's changing as time passes? Yeah, L is changing because the bar is moving. So we get W and B are constants, so they can be pulled out. We just get W times B times dL dt. So that's the derivative of flux is just the width, the distance between tracks, times the magnetic field, which isn't changing, times not L, but how fast L is changing. And what do we call how fast that distance is changing? What do we call the derivative of distance?
Would it be velocity?
Yeah, the derivative of position is velocity. So dL dt can just be replaced with speed. So this gives us an actual expression for how fast the flux is changing. Width, which I think we know, 2 meters, times magnetic field, which we don't know, times the speed, which is 40 meters per second. So we can say derivative of flux is width, 2 meters, times an unknown magnetic field times speed 40 meters per second. So we now actually have some values. Multiply those together, we get 2 times 40 would be 80 meters squared per second as the magnetic field. So that tells us how strong the flux is, or how strong the derivative of flux is, which is also how much induced voltage we get. So we can just take that value and plug it directly into d flux dt in Faraday's law, and get induced voltage is 80 meters squared per second times the magnetic field. And we still don't know the magnetic field, but this does tell us the induced EMF, the induced voltage, is 11 megavolts. So we could replace delta V induced with 11 megavolts equals 80 meters squared per second times magnetic field. And then how would we solve for magnetic field here?
Would we put a negative sign in front of it, or does that matter?
In this case, I wouldn't bother because the negative sign is basically talking about direction. In this context, we're basically just looking at magnitude. We don't really care about direction yet. We're just looking at how strong is the magnetic field, how strong is the induced voltage. So this is less about direction and more about absolute value.
Oh, is that also epsilon? Delta V?
Yeah, the epsilon here, the EMF or the epsilon, that's the same epsilon that we look at in as like the voltage of a battery in 7B. So this is just another notation for the induced voltage.
Okay.
Write it as epsilon or as delta V. The epsilon just means how much voltage boost is being provided. In this case, not by a battery, but instead by the changing flux.
Okay.
So we know that that in this case is 11 megavolts. Mega meaning 10 to the 9th, I think. No, 10 to the 6th million. Yeah. So that's 11 million volts. 11 times 10 to the 6th. And then how do we isolate B here? Yeah, divide by 80. So we've got 11 megavolts, in other words, 11 million volts, divided by 80 meters squared per second. So 10 to the 6th. So that'll be 11 million divided by 80, same as 1.1 million divided by 8. So that'll be 137,500. And the units for that would be, what do we have there? How else could you write out volts?
Joules per second?
Joules per second would be watts, the unit of power. Volts is an energy density. It's how much energy is packed into each unit of charge. So that's the, yeah, joules per coulomb. So joules per coulomb. And if we take joules divided by meters, because we are dividing by meters and meters again, joules could be written as Newton meters. So we get Newton meters per coulomb. One of the meters cancels out. So we're going to get Newton seconds in the numerator divided by, and then we're left with Coulomb meters in the denominator. And that's just another way of writing Teslas. So we could say magnetic field is 137,500 Teslas, which is an absurdly strong magnetic field, by the way. But that would be the magnetic field that would be required in order to make this arrangement provide exactly 11 million volts. Any questions on that?
How do you know that the angle is not changing in this scenario?
The angle would only be changing if the magnetic field were changing direction or if the surface itself were rotating. But in this case, we're not rotating the surface. We're not changing the direction of the magnetic field. All we're doing is making the area larger by moving this bar.
Okay.
So the angle doesn't change. The angle is 0 degrees and stays 0 degrees. The width isn't changing because we're not moving the bars, the rails further apart or closer together. And magnetic field is not changing either. All we're doing is making the area larger by moving the bar. And that becomes the derivative of length becomes the speed that the bar is moving. Any other questions on that one? And was there anything else we needed to figure out there? Direction of the induced current. And here's where we would need to take into account that negative. The negative in Faraday's law, you can think of as meaning the opposite direction. That the induced voltage, and therefore the current caused by the induced voltage, is going to be in a direction opposite to the change in flux. And what's happening to the flux here? Is the flux increasing or decreasing?
Flux is increasing out of the page.
Yeah, flux is increasing, and we would treat that as out of the page because that's the direction of the normal vector we chose. Flux,
Oh,
what was that?
no. So when we look at whether flux is like the direction where flux is increasing in general, we look at only like which direction the normal vector is pointing in.
Yeah. And this, I think, is the main reason why it's important to choose a normal, or at least a good idea to choose a normal vector that already mostly agrees with the magnetic field. If you were to choose the opposite normal vector, you'd still get the same result overall, but you, instead of having a positive value that's increasing, you'd have a negative value that's decreasing, and you'd have to take a look at the opposite direction, and it just gets really confusing. So I would use the normal vector that most closely agrees with the existing magnetic field. We know the flux is increasing, so we can treat that as a change in the direction of the normal vector. Like if you think of this as the normal vector is pointing outwards, so you can think of the flux as being outwards as well. Flux is technically a scalar, but you can think of it as being in the direction of the normal vector for purposes of direction. So you've got the flux is outwards and getting larger and larger and larger. So that's overall an outwards change. So the change in flux is outwards. Let me write that. So delta flux is outwards. But the Faraday's law says that the delta voltage is in the opposite direction. The induced effect is opposite to delta flux. In other words, inwards. So the change in flux is outwards, but Lenz's law or Faraday's law says that the negative there says that it's an inwards induced effect. So outwards change in flux means an inwards induced effect, which means current flowing this way. So that'll be clockwise from your perspective. So that suggests current is going to flow clockwise around the loop as this happens.
Wait, sorry, could you explain how you got that again?
Yeah, you take a look at the direction flux is changing. Flux is increasing, so we treat delta flux as being in the direction of the normal vector. So delta flux is in the outwards direction, but there's a negative sign in Lenz's law, so that means opposite direction. And then the right-hand rule suggests, if you curl your fingers, current's flowing this way around the loop.
So it's counterclockwise. Oh, sorry, it's clockwise for that reason.
Right,
Okay.
from the perspective, that would be clockwise. And as also as one final check, you can say that current that is now flowing produces a magnetic field of its own. So the induced current produces its own induced magnetic field. And which direction would that new magnetic field be?
Into the page?
Right. And note that that is opposite to the change. The change is overall in an outwards direction. And so the induced effect is in the opposite direction from the change. That doesn't mean it cancels anything out. It's just that it's in a direction opposite to the direction of the change.
Can you explain what Faraday's law means again?
Yeah, Faraday's law, as written here, is just saying that if the flux is changing as time passes, you get extra voltage in the loop. And this is basically an amendment or a correction to the loop rule from circuits in 7B. In 7B, we were saying if you go around a complete loop of wire, what should all the voltages add up to?
The
Zero.
battery? Oh,
Including the battery. Like if you, let's say you go through a battery and some resistors and some capacitors and you get back to your starting point. All those voltage differences should add up to what?
It'd be 0, right?
Right. The loop rule says that all those delta voltages in the loop have to add up to 0. Maybe you've got plus something from the battery and minus something from the resistors and minus something from a capacitor. Those changes all have to add up to 0. They have to balance out. But that's technically only true if there's no changing magnetic flux. In 7B, we were looking exclusively at examples where there was no magnetic effects going on. But if there is flux, specifically if there's changing flux, Faraday's law is basically a correction to the loop rule. Faraday's law says that you do get a voltage difference in a loop. The voltage differences do not add up to 0. Instead, they add up to the rate of change in magnetic flux. That if there's flux, or if the flux is changing as time passes, then the voltages in the loop don't add up to 0. Instead, they add up to the derivative of flux. I tend to think of this as being almost like a tiny invisible battery, adding an extra plus voltage boost to the loop that wasn't already there. So if the flux is changing, then the loop acts like there's an extra tiny invisible battery. And the strength of that tiny invisible battery equals how fast the flux is changing. The negative sign, on the other hand, is just referring to the direction, that the induced effect is going to be flowing in a direction opposite to the change in flux based on the right-hand rule. So figure out which direction is the change in flux. Point your thumb of your right hand in a direction opposite to the change in flux, and the curl of your fingers tells you the direction current is going to flow as a result of all this.
one more question about this problem. How do you know if the coil of wire, like how it's oriented? For example, let me show you. How do you know if it's oriented like this or like this or like this?
1 moment. Okay, show me again.
Oh yeah, sorry. How do you know if the coil of wire is oriented like this or in the YZ plane? Like how are you able to figure out that it's oriented like this?
In this case, that's just because that's what's showing on the page, that it's just showing this loop of wire in the frame of the page itself. We just got this rectangle.
Oh, okay. The rectangle is what kind of gives it away. Okay.
Yeah, whereas if it had been oriented like this, it would probably be drawn as more sort of a one end closer to you and one end clearly further from you. And that can be very difficult to show in just a flat two-dimensional diagram. It would probably have to have some extra explanation just describing the situation in more detail.
All right.
But in this case, I would just say this is drawn as being in the plane of the screen or page itself. So I would interpret it as just being in that alignment. Any other questions on that so far? All right, then let's take a look at that next problem as well. What was that? Artie, what was the one you wanted to look at on that next practice final?
1 second. I believe I think it was the last problem again.
Okay.
Yeah, I wasn't really sure how to start it.
With the 2 loops of wire?
Yeah, like what that meant.
Okay, 2 loops of wire, loop 2 lying inside loop 1. And we're creating current through loop one. So presumably loop one is attached to a battery or a generator or something. And we have a graph showing the current in loop one. So let's assume that there's a battery or a generator or something attached to loop one.
So like it's in a circuit?
Yeah. And presumably we'll have to have a gap there so we don't get a short circuit. So presumably it actually looks something like this. Maybe we've got a battery or a generator or something, and we're causing current to flow in loop one. And
Right.
but it's not truly a battery because it's not providing a constant voltage. It's providing a voltage, causing a current that changes as time passes. We start with no current, and then we ramp it up to more and more current flowing. And it says a positive current corresponds to counterclockwise. So positive current means it's flowing counterclockwise, faster and faster and faster. And then we maintain a constant current for a while. And then we make the current get weaker and weaker and weaker and stop, and then start flowing in the other direction, getting stronger and stronger, and then stay constant for a while, and then get weaker and weaker and stop. So that this graph describes how the current in loop one is changing as time passes because it's hooked up to some sort of variable battery or generator. Any questions on that so far?
So then loop 2 has nothing to do with this graph?
Not directly. Loop 2 is not connected to loop 1 in any physical connection sense. It's not like wired to loop 1 at all. But loop 1 has current flowing in a loop. Current flowing in a loop is going to create what sort of effect? Anytime you've got current flowing, especially current flowing in a loop, what does that create?
An increase in the magnetic field?
Yeah, or I would just say a magnetic field in general. The existence of current flowing through wire, or charge moving in general, but especially current flowing through wire, creates its own magnetic field. So loop 1 creates a magnetic field by virtue of the fact that it has current flowing. That means there is a magnetic field in the interior region, which includes loop 2. So loop 2 experiences a magnetic field. If that field changes, then loop 2 experiences a changing magnetic flux, and that causes induced voltage. So we're going to get current flowing in loop 2, even though they're not physically connected. We get current flowing in loop 2 because the current in loop 1 creates a changing magnetic field. Any questions on that so far?
Wait, sorry, just to clarify what this question is saying is, so with the changes in current in loop 1, there's going to be changes in the magnetic field. So that's why we would have flux. And then loop 2 will like try to counteract that.
Yeah. That the current in loop 1 creates a magnetic field in the interior. Which also means flux in loop 2, or within loop 2. So loop 2 is experiencing magnetic flux because there's current flowing in loop 1. That alone wouldn't be enough to create any induced effect. But the important thing is loop 1 is experiencing changing current. The current changes in loop 1. That means that creates a changing magnetic field in its interior, which means changing flux within loop 2. And if the flux within loop 2 is changing as time passes, that means we can apply Faraday's law, that the derivative of flux tells you the voltage induced. That the derivative, that the induced voltage, or induced epsilon, is negative derivative of flux. So if we can establish that the flux is changing as time passes, then that means that loop 2 experiences this magical extra voltage as if it had a tiny invisible battery. The amount of voltage depends on how fast the flux is changing, And the direction of that voltage is opposite to the direction of change in flux. Any questions on that so far? So let's take a look at this timeline. We probably want to split this timeline up into important intervals where things are changing in different ways. What would be the first interval of time we want to look at?
From 0 to 4?
Yeah, from 0 to 4 seconds, we've got something important going on. From 0 to 4 seconds, how would you describe the change here?
The current is increasing, right? So
Yeah.
that means like B field would increase.
Yeah, and specifically in which direction?
It says that the current for loop 1 is going counterclockwise, right? So we would use counterclockwise for I.
Right. So counterclockwise, and if loop 1 has counterclockwise current, that creates magnetic field in which direction?
Out of the page?
Right. This outwards magnetic field is increasing. So we can say that the change is in the outwards direction. If the change is in the outwards direction, what does that tell you about the magnetic field or the induced voltage? If we've got magnetic flux changing in the outwards direction, then the induced voltage is going to be in which direction?
It would be into the page.
Right.
Is it always like going in the opposite direction, increasing? Because I know, like, I think there was like an example in lecture where the professor was talking about how you could just decrease the magnetic field in the same direction.
In general, the induced effect is going to be opposite to the change in flux. So whatever direction the flux is changing, the induced effect is going to be opposite to that.
Oh, okay.
So in this case, the magnetic field is changing in the outwards direction. The idea is it's an outward magnetic field getting stronger and stronger and stronger and stronger. So overall, the change is outwards, which means the induced effect has to be inwards. And inwards, using the right hand rule, if you point your thumb inwards and curl your fingers, you get a clockwise current. So that suggests that loop 2 is experiencing a clockwise current during that period of time. And note that that's opposite to the current in loop 1. Loop 1 is experiencing a counterclockwise current that's getting faster and faster. While that's happening, loop 2 experiences a clockwise current, opposite to the change. Also, the induced voltage is proportional to the rate of change in loop 1's effects. What can you say about the rate of change of the current during this period of time?
It's constant, the rate of change?
Right. We've got a linear function. That means it has a constant rate of change, a constant slope. And it's a fairly weak slope compared to some of the other slopes involved. So I would say current 2 is clockwise, constant, and fairly weak. Because the amount of voltage, and therefore the amount of current in loop 2, depends on how fast the flux is changing. If the current in loop 1 is changing slowly and at a constant rate, then the current in loop 2, the induced effect, is going to be constant and weak because it's a slow change. So while the current in loop 1 is in the process of changing, you get a constant weak current in loop 2. And that's specifically from 0 seconds to 4 seconds. So that's everything we know about that first interval of time. During that first interval of time, from 0 seconds to 4 seconds, current 1 is increasing counterclockwise. So magnetic field is outwards and increasing. That's a change in the outwards direction. Because of the negative sign in Faraday's law, that means delta V is going to be in the inwards direction. The induced effect is inwards, opposite to the change in magnetic flux. That means the current in loop 2 has to be clockwise based on the right-hand rule. Any other questions on that so far? And what's the next important interval of time we should consider?
4 to 6 seconds.
Yeah, if we take a look at this interval from 4 seconds to 6 seconds, we can describe that in the same sort of terminology. What's happening to current 1 during that period of time?
The same amount of current
Right.
is
We've
flowing.
got current 1 is just staying the same. It is creating a magnetic field, but is that magnetic field changing?
No.
So that
We
means
can
that there's
say-
no flux.
Exactly. Well, there is flux, but that flux is constant.
Oh, right. You need changing flux in order to have induced current.
Exactly. Because the induced voltage and therefore the induced current is all about the derivative of flux as time passes. If the flux is constant, because the current that's causing it is constant, the constant flux means the derivative is 0. And if the derivative is 0, we get no induced voltage at all. So that means the current in loop 2 is 0 the whole time, from 4 seconds to 6 seconds. So as soon as the current, while the current in loop 1 is changing, we get current flowing in loop 2. As soon as the current in loop 1 stabilizes and stays constant, as soon as it stops changing, there's no current in loop 2 at all. There's only current in loop 2 during a period of time while loop 1 is changing its current. Are there any other periods of time that match that description?
From 10 to 12.
Yeah, looks like from 10 to 12, we've got the exact same thing. 10 to 12, there's current, but the current is not changing in loop 1. So that means you get no current in loop 2. And also looks like at the very end from 13 to 14 seconds. So in all those intervals, we've got no current. So in those 3 periods of time, 4 seconds to 6 seconds, 10 seconds to 12 seconds, and 13 seconds to 14 seconds, in all 3 of those intervals of time, we know that the current in loop 2 is 0. Any questions on that so far? And it looks like that just leaves us with 2 other periods of time to consider. From 6 to 10. And we could split that up from 6 to 8 and from 8 to 10. But since it's all just this continuous change, we could deal with all that in one analysis. During that entire period of time, what's happening to the current in loop 1?
Does the positive and minus matter? Because then that would mean that the current changes, right?
Yeah, let's start by taking a look at just from 6 to 8 seconds then. And then we'll see if we can extend that to 8 to 10 seconds. From 6 to 8 seconds, we still have counterclockwise current. So during that period of time, from 6 to 8 seconds, the current 1 is decreasing counterclockwise. And counterclockwise current means we still have an outwards magnetic field, but it's decreasing. So that's a change in which direction? If you've got an outwards vector, but it's decreasing, which direction is the change?
It would be in the opposite. Oh, sorry. It would be in the same direction, right?
Just the change. Which direction is delta flux? Yeah, that's going to be inwards, right? If you got an outwards vector and it's shrinking, the change is in the inwards direction. So we can say delta flux is inwards.
Are you saying that it increases in the inward direction?
Well, it's not an increase. It is the magnetic field is decreasing. But if you got an outwards pointing vector that's decreasing, the change is in the inwards direction.
Oh, okay.
Just like, for instance, if you got an upwards vector that's getting weaker and weaker and weaker, the change is in the downwards direction. If you got a vector pointing to your right that's getting weaker, the change is to your left. If you got a vector pointing outwards that's getting weaker, the change is inwards. So the overall change, and therefore the change in flux, counts as being in the inwards direction. But again, there's a negative sign in Faraday's law, so that means that the change in voltage in loop 2, the induced delta voltage is in the opposite, the outwards direction. And based on the right-hand rule, an outwards delta voltage means a counterclockwise current. So inwards change means outwards delta voltage induced, which means counterclockwise current. Any questions on that so far? And also, since this is constant slope, constant rate of change means constant amount of voltage. D flux dt is a constant value, so the induced voltage is also a constant value. It looks like that slope is a little bit steeper than it was from 0 to 4 seconds. So that suggests a stronger current, let's say a medium amount of current. So from 6 seconds to 8 seconds, we've got counterclockwise current in loop 2 and a constant strength, which is medium, a little bit stronger than the weaker current from 0 to 4 seconds. Any questions on that so far? And what about from 8 seconds to 10 seconds? From 8 to 10, which direction is the current in loop 1?
It's going clockwise now?
Yeah, we've got a clockwise current that gets stronger and stronger and stronger. Clockwise current means magnetic field pointing in which direction?
Into the
curl your
page?
finger, yeah, you curl your fingers clockwise, you get magnetic field pointing inwards. So from 8 to 10, we've got an inwards magnetic field. And is that getting stronger or weaker?
Stronger?
Yeah, so that means that's an inwards change. So that means the magnetic field is going to be inwards and getting stronger and stronger and stronger. That suggests a change in the inwards direction. But it looks like a change in the inwards direction is exactly what we were looking at from 6 to 8 seconds. So from 6 to 8 seconds, we've got a change in the inwards direction. From 8 to 10 seconds, it's still a change in the inwards direction. So we can actually treat 6 to 8 seconds and 8 to 10 seconds as effectively the same. Whether it's a positive value getting weaker or a negative value getting stronger, those both count as a change in the same direction. So they can be treated as identical. So it looks like the fact that that's a continuous negative slope, the same negative slope the whole time, means 6 to 10 seconds is just going to be one unified pattern. It's not like 8 to 10 seconds is meaningfully different than 6 to 8 seconds. So I think it's safe to say that I2 is counterclockwise and constant and medium strength from 6 seconds all the way to 10 seconds. Any questions on that so far?
So the reason you combine the two intervals for 6 and 10 is because the induced current is pointing in this, is like going in the same direction, like it just matches up everything?
Yeah, exactly. Then ultimately it doesn't matter if we've got, like from 6 to 8, we've got an outwards magnetic field that's decreasing. From 8 to 10, we've got an inwards magnetic field that's increasing. So if you've got an outwards magnetic field that's decreasing, that's a change in the inwards direction. It gets to 0 and it starts increasing in the other direction. That's still an inwards change. So it doesn't really matter whether it's like, if you have a positive number that's getting smaller, that's a change in the negative direction. If you have a negative number that's getting bigger, that's also a change in the negative direction. So it still has the same effect. So it looks like from 6 to 10, we have this unified counterclockwise current in loop 2. And note that that's exactly opposite to the slope here. We're treating positive as counterclockwise. From 6 to 10, we have a negative slope. So that suggests a clockwise effect, but the negative sign in Lenz's law reverses that, so we get a counterclockwise current in loop 2, treating that as positive. And then from 10 to 12, we've got no change and therefore no induced current. What about from 12 to 13?
The current is decreasing, or sorry, increasing, right?
Yeah, even though it's a negative value that's getting weaker, but mathematically we can treat that as an increase. And in fact, that matches the increase from the first 4 seconds. That even though it's a negative number getting close to 0 rather than a positive number getting further from 0, mathematically those both have positive slopes. So we should expect them to create negative induced current. And again, this goes back to the negative sign in Lenz's law. The induced effect is the opposite, at least in terms of direction. The induced effect is the opposite of the slope of the thing that caused it in the first place. That if you have a positive slope for the source current, we should expect a negative value for the induced current. If you have a negative slope for the source current, you should expect a positive value for the induced current. So from 12 to 13 seconds, we should expect a negative current, that is current in the clockwise direction in loop 2. Also, how does this slope compare to the other slopes?
It's the steepest.
Yeah, that's very steep. It's a very fast rate of change. And a fast rate of change means a very strong induced voltage, and therefore very strong induced current. So I think what we can conclude for that section is that from 12 to 13 seconds, we're going to get a very strong constant clockwise current in loop 2.
Wait, sorry, how do we know it's clockwise?
In part from the signs, based on the idea that we've got a positive slope. So current 1 has a positive rate of change, but the induced voltage is opposite to the rate of change. So mathematically, if we've got a positive slope, a positive rate of change for current 1, we should expect the induced effect to be in the negative direction. And negative in this context means clockwise, because we were treating counterclockwise as positive.
Oh, okay.
We could also look at this in terms of magnetic field. Loop 1 currently has a negative current, which means clockwise. Clockwise current means inwards, clockwise current, yeah, it means an inwards magnetic field. So we could also look at this as current 1 is getting weaker. It's decreasing clockwise. So the clockwise current creates an inwards magnetic field, but that's getting weaker, decreasing. If it's an inwards magnetic field but getting weaker and weaker and weaker, that's a change in the outwards direction. Change in the outwards direction. So overall, we're looking at a change in the outwards direction. So delta V is inwards. We got a change in the outwards direction. So the delta V is in the inwards direction, and inwards, curl your fingers, means clockwise, which agrees with the idea that a positive rate of change suggests a negative induced effect because of the negative sign in Faraday's law. Any questions on that so far? So let's see if we can use all this information to build a graph of current 2. Let me move this aside. So just taking a look at the information we now have. We know that we've got to have a constant weak current in the clockwise direction, which we're treating as negative, from 0 to 4 seconds. So from 0 to 4 seconds, we're going to have a constant weak magnetic field, or constant weak current, negative, representing clockwise. What about from 4 to 6 seconds?
Would it just be like at 0 from 4 to 6?
Right. From 4 to 6 seconds, we have no current, no induced current, because there's nothing changing. Likewise, from 10 to 12, and from 13 to 14. Because those were periods of time when the current in loop 1 wasn't changing. Therefore, the magnetic field is not changing, and no change in magnetic field, that is, no change in magnetic flux, means no induced voltage. So from 4 to 6, from 10 to 12, and from 13 to 14, there's no change in flux, and therefore no induced current at all. Induced current only happens while the flux is in the process of changing. What about from 6 seconds to 10 seconds? What do we know about it in that case?
Counterclockwise, and it's probably going to be stronger than what we set 0 to 4.
Right, we've got a medium constant counterclockwise current, and counterclockwise we're treating as positive. So we'll have a constant positive value stronger than it was between 0 and 4 seconds. So let's maybe mark that as 2. And what about from 12 to 13?
It's strong.
Yeah, strong, and also we said it was clockwise during that period of time. So a strong value that's negative and constant. So maybe something even further down, maybe down here. So this would be maybe not the most accurate of graphs, but at least a general idea of what sort of values, the fact that it's going to be constant during each of these intervals of time, and relatively how strong they are. So we're going to get a weak clockwise current from 0 to 4, no current at all from 4 to 6, a medium counterclockwise current from 6 seconds to 10 seconds, no current from 10 to 12, a sudden burst of very strong very strong clockwise current from 12 to 13 because of the sudden change, and then no current after that because there's no further change. Any other questions on that? Specific values for current 2. I don't know if we would need more information to calculate the exact values. We need to know things like how much, I guess we do know how much current there is in loop 1. We need to know things like what's the area of loop 2, how much of the area is enclosed there. We'd also need to know what's the resistance. Because even if you did know the area and the rates of change, you could find the voltage, but voltage equals current times resistance. So we need to know the resistance in loop 2 also. We could at least get relative values, though, by looking at the comparative values of slope. Like if you actually measure the slope of these lines, looks like we've got over 4 up 2, so that's slope 1/2. And then this looks like slope 1, and then slope 2. So 1/2, -1, and 2, we could actually use those just as values. If we mark this as 1/2, 1, and 2, that way we've at least made the induced current proportional to the slopes of the source current. Because the induced effect, the amount of induced current should be proportional to how fast the source is changing. So the value, in fact, this is almost like just graphing the derivative. The value of the induced current should be proportional to the negative derivative of the source current. So in a sense, this is almost like making the position, velocity, acceleration graphs back in 7b. We're making a graph whose value corresponds to the slope of the previous graph. Any other questions on that? Or any other examples you'd like to work on? Any other topics, any general questions, any specific examples you'd like to try out?
Do you have any examples where we have to like use a vector stuff and vector calculations?
Like for electric field or magnetic field or what?
I mean, magnetic fields would be better because I haven't seen any vector stuff for magnetic fields, only for electric fields.
I guess for magnetic fields, the calculation would probably involve something like maybe if you've got several wires and you want to combine the magnetic fields. Like if you've got several source currents that are all creating magnetic field, you would just calculate the magnetic field for each one individually and then add them together as vectors.
How would you break them apart into vectors though? Like into component vectors?
Well, you'd find the magnetic field vector from each one individually, from each source wire individually, using the formula for magnetic field strength, the mu times I over 2 pi r, to get the magnitude of the vector, and then you'd use the first right-hand rule to find direction. Once you've got each of those vectors, you want to add those vectors together, which generally is going to involve splitting them into xy components and adding up the components individually. And from that point onward, it works like any vectors. If you've got magnitude and direction, as long as you can write the direction as an angle, use sine and cosine to split that into x and y components. Once you've done that for each vector, you can just add all the x components together to get the total x component and add all the y components together to get the total y component. And then afterwards, I guess you would use Pythagorean theorem to find the magnitude of that total magnetic field, and inverse trigonometry, inverse tangent probably, to find the direction as an angle. Electric dipoles in bonds. What do you mean? Do you have an example of that?
I remember we went over it in DL, but I'm just trying to find where exactly it was.
Usually we define, like if you want to actually calculate the dipole moment, how much of a dipole it is.
I think it was that. And I think there was like a question on our quiz last week about that.
Typically what you want to do for that is calculate charge times distance. If you just got two charges that are equal, then the dipole moment is just going to be either one of those charges as an absolute value times the distance between them.
Yeah.
So that charge times distance tells you the dipole moment.
So if they're at like if we can assume that we have like a water molecule and it's kind of like in an L shape versus like more spread out like it usually is. I don't know how to explain it, but like the difference in like strength.
If you want to calculate the dipole moment of a more complicated shape, like let's say that water molecule, we'd have, so we're going to have a oxygen and a couple of hydrogens spaced some distance apart. And charges are where here? Which charges are on which atoms?
Like if this is water, the two smaller ones would be plus charges, and the larger one would be the negative one, right?
Yeah. So we're going to have plus, and I guess we could just call the amount of charge E for charge of the electron. So our charges are plus E plus E again, and then minus 2E. So those would be that's the charge distribution. And presumably these are connected by some sort of bonds. And it is reasonable to call this a dipole because we can draw in a hypothetical line that splits it into a half that's definitely positive and a half that's definitely negative.
Yeah.
So this is very definitely a dipole. We just need a way to calculate the dipole moment.
Yeah, my main point of confusion here was like, so I actually put a picture from the quiz that we took, and my question was, in that picture, there's like a molecule that has the bonds more spread out versus like more compact. So how do you know how do you calculate the dipole in each of the structures, I guess?
Well, in general, to calculate the dipole moment, you could just draw out a distance vector for each object in the system and multiply it by the charge at that location. And you have to pick a location to draw all the distance vectors from. And I'm not sure if there's a specific standard for that. I think you can just draw it from the center of mass or from the largest molecule or something like that. But if you take a look at these distances, we've got this distance times positive E, and this distance times positive E. So if we think of these as, let's say distance, let's just call this distance R. And then this one's going to be just another copy of R. The idea of dipole moment is you're multiplying distance as a vector times charge at that location. So we'd have some distance R times E. Because if we multiply this distance times this charge, we get a new vector in that location. So this is E times R. And then the other one, we've got another copy of E times R, but in the other direction. So this is another E times R. And we want to add those together. We're just going to add E times R plus this E times R. And also technically plus negative 2E times another distance, but that distance is 0 because we're basically treating the oxygen atom as the origin. So we'd have E times R up and to the left plus E times R up and to the right plus 0 because the oxygen atom is at, I guess you could call that the pivot point essentially. And when we add those, we can just add those as vectors, adding them head to tail. And so the actual dipole moment is going to be this. So this would be the dipole moment of the entire molecule, just by adding those together. And note that geometrically, that is pointing from the negative side towards the positive side, specifically from the center of the negative region towards the center of the positive region. but its magnitude is going to be found by adding E times R this way plus E times R this way as vectors. So if you want the actual dipole moment magnitude, you would need to use vector addition. Any questions on that so far?
Oh no, actually, I think I understand it now. Yeah.
So let's try applying that approach to those practice problems. Let me pull that up as well. Where we have some polar molecules and we want to rank them by the magnitude of the electric dipole moment. So if we try the same approach here, do electric dipoles align with magnetic fields? No, electric dipoles would not be influenced by magnetic fields at all, unless the electric dipole is moving. Because if the electric dipole is moving, then each piece of it counts as moving charge, which will experience a force from the magnetic field. And likewise, a magnetic dipole is not going to be directly influenced by an electric field. But an electric dipole will definitely align with an electric field. A magnetic dipole will align with a magnetic field. But they don't influence each other directly unless there's also motion involved. So let's see if we can evaluate what these magnetic field or these electric dipoles are going to be. We've got, like in part A, it looks like pretty much the exact situation we were just looking at. We've got distance vector times this charge q plus this distance vector times this charge q. Let me actually make those a little smaller. So we've got distance vector times whatever that charge is, and the same distance, just in a different direction, times the same charge. And then if we treat the negative 2q as the origin, then we got negative 2q times 0, so we can ignore that. So we've got those vectors added together, and we're now going to have this as the dipole moment. So that is P, the dipole moment vector here for object A. Any questions on that so far?
No, we would just do vector addition basically.
Exactly. And since we're just looking at this conceptually, we're not really trying to find any specific values. We can just add those together by putting them head to tail. Likewise for object B, notice it's the same charges. We're just having them in different locations. So we're still going to have a vector, the distance vector times the charge is going to be the same amount. And this distance vector, so distance vector times charge, something like that. If we add those together, again, putting them head to tail, and drawing a vector from start to finish, how does that compare with object A?
Is it more steeper, the dipole moment, like the?
Yes, steeper in the sense of a different angle, a different direction. But what about in terms of the magnitude? If we just compare those directly, what do you notice? Yeah, it's smaller. And the reason for that, if you take a look at the contributions that caused it, for A, we were adding these vectors together. So we've got purely x direction plus purely y direction. But for B, this vector was rotated more like this. So it has a smaller y component and it has an x component to the left. So what happens to the x components when we add those together?
It gets reduced.
Right, those are going to partly cancel out. So that means the dipole moment is weaker. Let's take a look at D then, while we're at it. In D, it looks like we've got the same distance. But what about the charges? How does this charge compare to this charge sling? Yeah, it's more charge, specifically 4 times as much. So instead of drawing out, I mean, we were thinking of this length, this magnitude as this bond distance, bond length times charge Q. If we're instead taking the same bond length times charge 4Q, it's going to be 4 times as long. And since that's the only charge involved, then our dipole moment is just going to be that value, that vector. So our dipole moment is just this whole thing. That would be dipole moment for D. So D is going to be a very large dipole moment because it's just these two charges. So we just got this length times that charge, but the charge is 4 times as much. So we've got an enormous dipole moment there. Any questions on that so far? And then for C, we've got a distance times a charge. I'm going to treat the positive 4Q as the origin here. We've got a distance, but we're multiplying that by negative 2Q. What happens to a vector if you multiply by a negative?
It switches direction.
Yeah, it's going to change direction. So that means the dipole moment, if we look at just the negative 2Q charge, the dipole moment is going to be an upwards direction times negative 2Q. That flips it to downwards. So we're going to have a downwards direction. And also, because it's 2Q instead of just 1Q, it's going to be twice as big. So we've got this large downwards vector. And likewise for the other one, if we draw a vector from what we're treating as the origin to the location of the other charge. But again, we're multiplying by negative 2Q, so it's going to be large and in the opposite direction. So something like that. And then we add those vectors together. We're going to get a large result, looks like down and to the left. So that would be, that diagonal would be the dipole moment for vector, for dipole C, object C. So object C looks like it has a dipole moment that is larger than dipole moment for object A, but I think that's going to be weaker than for object D. Yeah, that does look smaller. And I think D is going to be the largest because even though D has the same amount of charge as C, we've got a 4Q positive charge and negative 4Q negative charge. Here we've also got positive 4Q and overall negative 4Q. But what's different about D versus C? What differences do you notice there between object C and object D?
The direction?
The direction, yes, but if we just rotated that, it wouldn't really make a difference, right? Like if we just took object D and rotated it so it aligned with object C, they still wouldn't be the same. So direction is not the only thing that matters here. What's the other big difference between object C and object D?
Object D has no Y component.
That's still just about direction though. Let's say we spin object D around so that we have, let's say we've got a positive charge here and a negative charge here. And then a connection. So let's say all we're doing is we're rotating object D, so it now looks like this. It's oriented exactly the same as object C. And we have positive 4Q and a negative 4Q. So same orientation, but what's the big difference between object C and object D? They both have 4Q worth of positive charge. They both have a total of 4Q worth of negative charge. But what's really the difference there?
The magnitude of the dipole moment.
And why is that? I mean, if you're just arranging 4Q worth of positive charge and 4Q worth of negative charge, what's the difference in the arrangement that leads to D having such a large magnetic or larger dipole moment? Where is the charge located at C versus where is the charge located in D?
I mean, the charge in C, it's like the negative charge is split between two molecules.
Yeah, it's more spread out, right? Like in C, you've got a bunch of positive charge here, some negative charge here, some negative charge here. In object D, you've got the same amount of charge, but we're taking those negative charges and mushing them together. The fact that those negative charges are concentrated in one location kind of combines their effect in a more efficient way. So in object C, the negative charge being more spread out makes it a weaker effect. But in object D, the negative charges being combined in one small location makes it a stronger overall effect. And I think you can see somewhat of the same thing with A and B. In object A, those positive charges are spread out. In object B, they're even more spread out, so it's a weaker weaker electric dipole. So I think to get a very strong electric dipole, you'd want lots of positive charge concentrated in one location, lots of negative charge concentrated in another location, and spread out very far from each other. Whereas if the positive charge is more smeared out or the negative charge is more smeared out and they're close together to each other, that's going to be a weaker dipole moment. Any other questions on that?
So you said you want the charge to be concentrated, but also you want the positive and the negative charge to be as far as possible from each other?
Yeah, I think the strongest dipole moment is going to be if the positive charge is just one small concentrated location and the negative charge is one small concentrated location, and those two locations are far apart from each other. That's going to lead to a strong dipole moment in terms of just magnitude. And then direction is all about which direction it's oriented. If you rotate the object, you're also changing the direction of the dipole moment. But overall, the dipole moment should point from the average location of all the negative charge towards the average location of all the positive charge. For example, in object A, you've got a negative region and you've got a positive region. The dipole moment points from the middle of the negative region towards the middle of the positive region. Object B, you've also got a positive region and you've got a negative region. The dipole moment points from the center of the positive region towards the center of the negative region. Even in object C, for instance, you've got a positive region and you've got a negative region. And the dipole moment points from the center of the positive region towards the center of the negative region. The actual magnitude is determined by both how much charge and how it's distributed and how far apart it is. But the direction should always be from the middle of the positive region on average towards the middle of the negative, or from the negative region on average towards the positive region on average. Any other questions on the dipole stuff? Okay, and what else do we have here? Radhika, you've got a magnetic dipole problem. Let me pull that up.
Yeah.
So we've got a current carrying wire into the page. We've got a magnet, presumably a magnetic dipole, just a bar magnet. And we want to know what's going on here. First of all, can we get a direction for the magnetic field caused by this current carrying wire?
So, okay, the reason why I was confused with this
Yeah.
problem is because I started like trying to do right hand rule number one, but then I realized that you can't use right hand rule number one for these types of problems where, because that only works for current if the source is a current.
Well, we do have a current here. We've got current in the wire here. Although we want to look at the magnetic force on the wire, so that is going to change things.
Yeah.
So what is the source here? I mean, if we treated the wire as the source, then yes, current would be going clockwise around the wire, or sorry, magnetic field clockwise around the wire. But in this case, it looks like we're looking for the force on the wire. So if we're looking for the force on the wire, then we're treating the wire as the test object. And instead we should be looking at what's the source here? What's causing the magnetic field?
The magnet.
Right, this bar magnet here, this permanent magnet, is a magnetic dipole that's creating a magnetic field. So in this context, we're treating the bar magnet as the source, creating a magnetic field. And then we're going to look at the wire with current as the test object, experiencing a force from that magnetic field. So let's see if we can draw out the magnetic field caused by this bar magnet. We should expect the typical sort of curved loops for the magnetic field, because this is a dipole. And specifically, those magnetic field vector, the magnetic field lines should be curves going from where to where.
North to south, I think.
Yeah, the magnetic field lines should be coming out of the north end and going towards the south end. So we should expect magnetic field lines out of the north end and inwards towards the south end. And curving around, something like this. And below as well. And this is just a rough sketch. This should be more symmetric than this. But the important thing overall is the directionality, coming out of the north end and going into the south end. And if you wanted to look at what's going on inside as well, these would form complete loops. Except for, of course, the straight line through the middle. So the magnetic field lines caused by this magnetic dipole, this bar magnet, would look something like this. But we don't really need to care about the entire magnetic field. We just care about at the location of the test wire. At that location, at the location of the test wire itself, magnetic field is to the right. So that's the magnetic field vector. And we now have magnetic field to the right, and we've got current flowing into the page, the test current. So how could we figure out the direction of the force on the wire?
So now we can use right hand rule number two.
Yeah, second right hand rule, using usually thumb for motion of the charge. In this case, the motion of the charge is just the current. So you point your thumb of your right hand in the direction current is flowing. So that's going to be into the screen. Point your first finger in the direction of the magnetic field itself. So that's to your right. And your middle finger should tell you the direction of the force on that wire. So I think that's going to be a downwards force in this case.
Yeah, it should be a downwards force.
Yeah. So this wire experiences a downwards force. Any questions on that one? Or anything else you want to work on? You're welcome. Any other topics or questions you'd like to go over before we go? All right, then I'm going to call that good for now. I will continue to have office hours tomorrow and Thursday. The hours and link are posted on mathandcheese.org as usual. So feel free to stop by if you have any other questions. Good luck on finals, and I will see you later.